We have an illustrious cast for the morning today, but starting us today is Sue Sierra from the University of Edinburgh, who I'm super excited to hear talk about enveloping algebras and infinite dimensional Lie algebras. Take it away, Sue.
Great. Well, thank you, Tyler. Thank you, all the organizers, for putting together this meeting, which is just amazing to see happening, and for inviting me and for making it possible for people to participate virtually as well as in person. Mathematically, I've really enjoyed the conference so far. I've not made it to all the talks, but the talks I've been to, I've learned a lot. It's been very interesting. I'm jealous that I'm not able to really be there in person and participate in the community building, because it sounds like it's going to be great. And Tyler is telling me that this is going to happen again, so I'm looking forward to it. So greetings from Edinburgh, where the blind behind me is closed so the afternoon sun isn't shining into everyone's eyes. What I want to tell you about are some very interesting non-commutative rings related to infinite dimensional Lie algebras, which I've been thinking about for the past few years. There surprisingly little is known about these. They're very cool, they're very mysterious, and I'm hoping that I can get you interested in them. So this title is a bit of a mouthful. So I have an alternate title, which is just big enveloping algebras. You know, big Lie algebras, you turn them into big rings. And what I'm planning, this is what I'm planning to do in the talk. I want to start slowly and friendlily. I'm not sure, the talks I've been to so far have all been commutative algebra. I'm not sure how much non-commutative algebra has happened at the conference so far. So I thought I would have a gentle introduction to what I'm doing. But at the end in the second half of the talk, there's going to be lots of new results and also lots of open questions, because this is a very, in a lot of ways, a very wide open area. But first of all, in the spirit of community building, and since I'm not there in person and can't sort of hang out with people at the coffee hour, I thought I'd lead off with some pictures. So I would never, ever in a million years usually put this picture in a professional talk. This is this is my wedding in 2004, so quite a while ago. But how else could I was trying to think of an image that would inject some good queer content into this talk, and this seemed like the best I could do. The other pictures I wanted to show are sort of basically a lot of my co-authors. These are people that you'll meet throughout this talk. And I like putting the photos of mathematicians up there to get some faces attached to the names. And I also I felt like this was a nice picture to put up at a conference that's dedicated in some ways to, diversity within mathematics. So we'll meet these people again throughout the talk. But maybe you want to remember some of these names. Okay, so on to the mathematics. Let's start by talking just about Lie algebras, which are clearly part of the picture here. So the example I want people to keep in mind is this object called the Vit algebra. So it's derivations on Laurent polynomials in one variable, and I'm always going to write it as the Laurent polynomial ring times the symbol del. So here del always means differentiation with respect to t, and a derivation here, as a reminder, this is a linear map from the ring to itself that obeys the Leibniz rule. So if you want to remember your sort of one variable calculus days, from high school, this is helpful in this talk. So this is called the Vit algebra, but in what sense is it an algebra, right? Usually an algebra is an associative ring that contains a field in its center. But here, so what properties does this have? Well, first of all, it's not commutative. And basically, this is because of the product rule in calculus. So if you differentiate GH, of course, that's GH prime plus G prime H. And you can think of that as the operator G times del plus G prime acting on H. So here a polynomial acts on another polynomial just by multiplication. So what this tells you is that del G is G del plus G prime. So this is definitely a non-commutative situation. That's fine. More worrying for calling the Vit algebra an algebra is that it's not clear what operation it's closed under. It's not closed under composition of operators, right? F del composed with G del. Well, del G is G del plus G prime, so work this out, and it's got an FG del squared in it. But everything in the Vit algebra nothing in the Vit algebra has a del squared. So we've got to have another way to combine elements of the Vit algebra. And the problem is FG del squared, and you can get rid of that by subtracting off G del F del. And when you do that, you get that the commutator of F del and G del is another Laurent polynomial times del. So it is an element of the Vit algebra. So this operation, taking the commutator of two of these, is an operation where the algebra does have closure. So let's look at some of the properties of it. We'll call it a bracket, right? So F del G del is their commutator. If you like, we'll just define it by the formula. It's Fg prime minus F prime G. It's not associative. It's bilinear. It's antisymmetric. And then if you start taking brackets of three things and combine them together, there's a dependence relation. This is called the Jacobi identity. So these properties are, they show up a lot, and they give W the structure of a Lie algebra. In fact, what I've got here is the definition of a Lie algebra over the complex numbers. It's got this bracket that's antisymmetric, bilinear, and satisfies the Jacobi identity. So why would you care about Lie algebras? Well, they show up all over the place in mathematics and in physics. So just some examples to show that even if you've never thought about these before, you know a lot of them, right? N by N matrices are a Lie algebra under commutator. They're the sub-algebra of traceless matrices, SLNC, is also a Lie algebra. If I have any vector space, I can make it into a Lie algebra by declaring the bracket to be 0. This gets called an abelian Lie algebra because we're thinking the bracket we think of usually as coming from a commutator, and if it did, then the vanishing of the bracket would precisely say that the algebra it came from was abelian. And then more generally, if you've got any Lie group, so this is a manifold that also has a group structure, then you expect to have some algebraic structure on the tangent space to the manifold at the identity. And the structure you have is the structure of a Lie algebra. So this Lie algebra structure is a very natural thing to think about. But all of these examples on this page, maybe with the exception of this V, are finite dimensional. And I said I was thinking about infinite dimensional Lie algebras. So let's have some infinite dimensional examples. Well, the Vit algebra, which we met, right? That's sort of where we derived the rules for something to be a Lie algebra. Another, if you take any Lie algebra, let's call it G, and right now let's think G is finite dimensional. Then you can create an infinite dimensional Lie algebra called the Loop algebra by tensoring it with Laurent polynomials, or actually with any commutative ring. So what's the bracket of X tensor F with Y tensor G, where X and Y are elements of the underlying finite dimensional Lie algebra? Well, we combine X and Y in the only way that makes sense, with the Lie bracket on G, and we combine F and G just by multiplication. And this gives this vector space a Lie algebra structure. I also want to talk about these very interesting central extension of the Vit algebra. So this is called the Virasoro algebra, it's one of these objects that's sort of ubiquitous on in mathematics, a bit like Dinkin diagrams. It just shows up all over the place, even in places where you might not expect it. And it also shows up a lot in physics, particularly in conformal field theory. So as a vector space, the Virasoro algebra is just, take the Vit algebra and then add on a one-dimensional vector space, which is going to be generated by Z. But it has a Lie algebra structure. And the Lie algebra structure is that Z is central. That is, its bracket with anything is just 0. And then when I bracket two elements of W, so some F del and G del together, well, I have the bracket on the Vit algebra, and then I also get something times Z. And I've given a particular formula for it. It doesn't really matter what the formula is. The point is that this does satisfy the needed conditions for the Virasoro to be a Lie algebra. The condition for this central extension to be a Lie algebra is really a condition on, you've got a function from two copies of W to the complex numbers. It's what is the coefficient of Z you get when you bracket them together. And this function turns out to live in some cohomology group. It's a 2 cocycle. And you can, in fact, compute the second cohomology of any Lie algebra and thereby classify central extensions. One other example I wanted to do is another central extension. So you can do this actually for any finite dimensional simple Lie algebra G, but I'll just write it down for SL2. So this is what gets called an affine algebra. And again, it's a central extension of something. It's a central extension of the loop algebra. So I haven't given you the Lie bracket here. Again, there's going to be some cocycle that makes this non-trivial central extension. In other words, you get some interaction with Z and the other stuff in the Lie algebra. And the cocycle, which I haven't written down, turns out to be, for people that have seen Lie algebras before, it turns out to be built on the invariant bilinear form on G, the killing form. So this means that you need to have maybe a nice underlying Lie algebra G for this to work, which is why I'm requiring here that G be simple. But for the purpose of this talk, let's just think of affine SL2 is some central extension of the loop algebra of SL2. And I won't worry too much about the details of what it looks like. Okay, so that's Lie algebras done at lightning speed. I should say one of the difficulties of giving online talks, right, is having a very hard time telling how it's coming across to the audience. So please, if people have questions, please stop. Please stop me. Please raise your hand. Please ask on the Zoom. And I'm happy to pause the talk and answer them. Okay, so we had a lightning introduction to Lie algebras. What about enveloping algebras, which are supposed to be the subject of this talk? Well, I should be calling these universal enveloping algebras, but my title is already long enough, so I've left out the word universal. And what a universal enveloping algebra is, it's a machine for converting a Lie algebra into an associative algebra. So take any Lie algebra, let's call it fracture G. Then the universal enveloping algebra of G is, well, I'm going to take the tensor algebra on G, that is the free algebra, all non-commutative polynomials in some basis of G. And then the relations I'm going to oppose is that in this universal enveloping algebra, the commutator of two elements of G is the same thing as the Lie bracket. So what does this look like? Well, let's do an example for SL2. So a basis for SL2, this is the usual basis for SL2. I just write down the upper triangular nilpotent traceless matrix, the lower triangular one, and then 1 minus 1 on the diagonal. So what's the enveloping algebra? Well, let's think of it as non-commutative polynomials in these three generators, E, F, and H. But I've rewritten the relation slightly. So I have Fe is EF minus H just by moving, I had this YX and I moved it over here. HE is EH plus 2E, HF is FH minus 2F. So what this does, right, is let's say I always want to write my elements E, F, H in that order. But a priori, this is a non-commutative ring. I might have a word in here where the elements appear out of order. Right? But if I have a word which has an F before an E, right, then I can use this relation to swap the E and the F. And likewise, if I have an H and an E out of order, I can use this relation to swap the H and the E, etc. So the basic structure theorem for these universal enveloping algebras is something called the Poincaré-Birkhoff-Vit theorem, or the Pbw theorem for short. And it says that what you might think from what I was saying on the previous slide is actually true. The monomials e to the I, f to the j, h to the k, with e, f, h sort of in the right order, are actually a basis for USL2 over the complex numbers. And likewise, if we're working with the Vit algebra, again, let's take a nice basis. Let's look at t to the n plus 1 times del. We'll call that e sub n. And in the enveloping algebra, the commutator of en and em is the same thing as the bracket, the Lie bracket of en and em, which works out to be m minus n times en plus m. So again, this gives us a way to rewrite monomials where the generators appear out of order. And what it says is that a basis for the enveloping algebra of the Vit algebra is monomials that look like some power of n1, some power of some bigger n2, on out to some power of some bigger nk. So they're sort of monomials written in increasing order. So as a recap, right, I have this Lie algebra. Well, I'm actually a ring theorist. I want to work with non-commutative rings. I turn it into a non-commutative ring by forming this universal enveloping algebra. And this doesn't actually do very much damage in some sense, because it turns out the representation theory of the ring, of the universal enveloping algebra and of the underlying Lie algebra are the same. So it's just that one of them is maybe in a situation where you can use ring theoretic tools, and certainly where my intuition is better. Okay. So what's known about enveloping algebras? Well, let's start with talking about a finite dimensional Lie algebra of dimension, say, d. So basically, the tagline is that the enveloping algebra here has all the nice properties of polynomials in d variables, but it's more interesting. So let me go through that. What are the nice properties? Well, one certainly nice property is that the ring is Noetherian. And for me, Noetherian means left and right Noetherian. So one-sided ideals of the enveloping algebra of a finite dimensional Lie algebra are finitely generated. It also has polynomial growth. So here, how am I going to measure the size of a non-commutative ring? Well, one way to do it is to take a finite dimensional vector space inside maybe my big infinite dimensional algebra, start taking powers of that vector space and measure the dimension of those powers. And in the case of this enveloping algebra, the fastest this dimension can possibly grow is a polynomial in n of degree d. So we say that this enveloping algebra here has polynomial growth. So, okay, so those are some two ways in which this enveloping algebra is nice. I said it was more interesting. I guess that's maybe a judgment call. There's lots of ways in which it's more interesting. Let me just say that the two-sided ideals in particular are very interesting and in general much harder to understand than two-sided ideals in a polynomial ring. And for these finite dimensional Lie algebras, these enveloping algebras are absolutely fundamental examples in non-commutative algebra. In fact, a lot of what are now basic techniques of non-commutative ring theory were developed to study enveloping algebras of finite dimensional Lie algebras. So they're very, very well understood. They're very well studied. There's some beautiful geometry underlying what they look like, and in particular, the structure of the two-sided ideals I was talking about. Okay, well, but what about infinite dimensional, which is what this talk is about? So these are these big enveloping algebras of infinite dimensional Lie algebras. Here, they're much more mysterious. So for me, again, a big enveloping algebra is just an enveloping algebra of an infinite dimensional Lie algebra. And the fundamental question in this subject is, can these ever be nice? Of course, you can't answer this question without some definition of nice. So what could we mean by nice here? Well, one way in which enveloping algebras of finite dimensional Lie algebras were nice was that they had polynomial growth. So here we lose. It's a theorem of Martha Smith back in the 70s that an enveloping algebra has polynomial growth exactly when the Lie algebra is finite dimensional. So just as an example, the growth of the Vit algebra looks like e to the square root of n. So this is faster than any polynomial, but still sub-exponential. So this gets called sub-exponential or sometimes intermediate growth. But certainly these big enveloping algebras are very, very large rings. They grow faster than any polynomial. So in that sense, they're not nice. Okay. What about other ways in which they might be nice? Well, one of the other ways in which enveloping algebras of finite dimensional Lie algebras were nice was that they were always Noetherian. And this is the fundamental question, I think, really in the subject. It was first asked in print, as far as I could determine, by Omayo and Stewart in 1974, although Lie theorists had wondered about it, I think, well before that. If you've got an infinite dimensional Lie algebra, is it possible for its enveloping algebra to ever be Noetherian? So let's get rid of some easy examples where it's obvious the enveloping algebra isn't Noetherian. So first of all, suppose you have an abelian Lie algebra. Well, then if you go back to the relations of the enveloping algebra, it said xy minus yx was the bracket of something. So for an abelian Lie algebra, that bracket's always 0. And so the relations are just going to be xy minus yx is 0. In other words, the enveloping algebra is just going to be a big polynomial ring. And we know very well that a polynomial ring is Noetherian if and only if it's a polynomial ring in finitely many variables. So infinite dimensional abelian Lie algebras, enveloping algebra is not Noetherian. That's boring. It's also easy to see that in general, if you have a Lie algebra that isn't finitely generated, then its enveloping algebra can't be Noetherian. So the question is only interesting for finitely generated Lie algebras, like these examples I've been showing you. So, okay, so you get rid of those easy non-Noetherian examples. And then the first obvious example you want to think about is the Vit algebra. So in 1990, Carolyn Dean and Lance Small, in a paper about the enveloping algebra, the Vit algebra, specifically asked, is the enveloping algebra, the Vit algebra, Noetherian? And this turned out to be a difficult question, and no one could answer it. So the subject sort of stopped, right? The first question you want to ask about a non-Noetherian ring, about a ring that you meet maybe in a dark alley somewhere, is the ring Noetherian? And people couldn't figure out the answer to this for the first non-trivial example. But it turns out, Chelsea Walton and I showed in 2013 that the answer is no. This enveloping algebra is neither left nor right Noetherian. And one of the remarkable things about this theorem is that the proof actually goes through, it's not, you don't have to construct some really out of the way infinitely generated ideal. Like the proof was sort of waiting out there for someone to notice all along, and yet somehow no one did until we came along in 2013. So how does the proof go? Well, let's take a ring I'll call A. This is a Vit algebra, or more technically, I suppose, a localized Vit algebra. So I'm being a bit naughty here. I'm writing it as polynomials in T, T inverse, and del, but it's a non-commutative ring. I still have the relation del T is T del plus 1 that we saw earlier in this talk, comes from the product rule. Now, by construction, right, I constructed the Vit algebra as a subset of this ring. And this means that turns out that this means that there's a ring homomorphism from the enveloping algebra to A, which on the Lie algebra just does the obvious thing. It sends F del to F del. The universal property of the universal enveloping algebra is that if there's a Lie algebra map from your underlying Lie algebra to some non-commutative ring, then you get a map from the enveloping algebra. So this Lie algebra map, which is just the identity on the Vit algebra, lifts up to a ring map from the enveloping algebra to this Phi algebra, and it turns out that the kernel of this map, kernel of Phi, it's a two-sided ideal, but if you think of it as either a left or a right ideal, it turns out not to be finitely generated. Once we proved that the enveloping algebra, the Vit algebra, was not Noetherian, a lot of other Lie algebras just came along for the ride. So the Virasoro algebra, remember, I built that out of the Vit algebra and one more central guy, Z. The Vit algebra, the enveloping algebra, Vit algebra is actually a quotient of U of Vir. So since U of W isn't Noetherian, there's no way that U of Vir could be. And more generally, from the Vit algebra, any Lie algebra that's infinite dimensional has polynomial growth and then is graded simple. So we need the Lie algebra to be Z graded, also turns out not to have a Noetherian enveloping algebra. Since this paper came out, a lot of other infinite dimensional Lie algebras have been looked at to see whether their enveloping algebras might be Noetherian. So loop algebras, affine algebras like SL2 hat that I defined earlier, infinite dimensional Kac-Moody algebras. I'm not going to define them, just a big class of Lie algebras of things people think about. My PhD student, Lucas Bazaglo, proved last year that you have the Lie algebra of vector fields on an affine variety. All of these, or none of these, have Noetherian enveloping algebras. And there are more examples, which I could have listed and just ran out of room on the slide. So there's no known example of an infinite dimensional Lie algebra with a left or right Noetherian universal enveloping algebra. So even back in 2013, Chelsea Walton and myself thought that, if this could be proved for the Vit algebra, it's surely true for general Lie algebras. So we conjectured that the only way for an enveloping algebra to be Noetherian is if the Lie algebra is finite dimensional. And this, I would say, is the fundamental open problem in the subject. And it's hard. In fact, it's too hard. So I'm going to do the classic mathematician bait and switch, right? I said I was interested in questions about these big enveloping algebras. The first question is, are they Noetherian?
You have a question?
Yeah, hello?
Hi, Sue. This is Renzo. Sorry, before you bait and switch.
Yeah.
Can I ask you, like, so this conjecture, I mean, would it just be sort of extremely surprising if you found an enveloping algebra which is Noetherian and G is interdimensional? Or would it also have sort of like some remarkable and weird applications that you expect to not be true?
It would certainly be extremely surprising. I would think it would have remarkable and weird applications. I mean, for Noetherian rings, the representation theory is much better behaved in general than non-Noetherian algebras. So it might give you more tools to look at the representation theory of these Lie algebras. But I'm not sure what the consequences would be, because I mean, I don't think there are any. So I haven't thought too much about what the consequences would be if I found one. You see what I mean? I think I'm mostly on the, wow, that would be bizarre.
There's no more questions in the room.
Okay, so I'm going to bait and switch since I can't answer this question. And instead, let me go back to the U of W example, and let's look at what was established about the behavior of U of W in investigating Noetherianity. And remember, I said that for finite dimensional Lie algebras, the two-sided ideals in the enveloping algebra are very, very interesting. So it's natural to start to think about two-sided ideals in U of W. So let's do that. And some very interesting facts emerge from the proof of the non-Noetherianity of U of W. So remember, the way that was proved was by looking at this ring homomorphism from U of W to this Weil algebra, right? And remember, the kernel of this map phi was the non-Noetherian one. This was the one that was infinitely generated as either a left or a right ideal. But it turns out, this is work of Conley and Martin, that as a two-sided ideal, it's actually principal. It's generated by just one element, even though it's infinitely generated on one side. Furthermore, the image of phi has ACC on two-sided ideals. And of course, the image of phi has polynomial growth. I'm sitting inside this Weil algebra whose growth looks like a polynomial ring. And once we observed that these properties got kernel of phi, we started to do some computer experiments. And they suggested, in fact, that all factor rings of U of W had polynomial growth. So this seemed bizarre. And in a paper of myself and Alexei Petukov in 2017, we conjectured two things about U of W. First of all, we conjectured that ideals are sparse. That is, that even though this is a non-Noetherian ring, if you look just at two-sided ideals, it satisfies the ascending chain on two-sided ideal, or the ascending chain condition on two-sided ideals. And we also conjectured that ideals, two-sided ideals, are big. So here I want to make a definition. Let's say a ring R has just infinite growth if the ring itself grows faster than any polynomial. But if I take any proper two-sided ideal of R, call it I, and factor it out, I get a ring that has polynomial growth. So this says that the ring itself is very, very big. It has infinite growth, but somehow any homomorphic image of the ring is controllable, has polynomial growth. And so we'll say that a ring like that has just infinite growth. And the conjecture that we made was that U of W has just infinite growth. So we made these conjectures back in 2017. 5 years have passed since then. Let me tell you what's known about these conjectures at this point. So we know very little more about the ACC conjecture at this point. So in our 2017 paper, what Alexei and I proved was that U of W satisfies the ascending chain condition on two-sided ideals, which are generated by quadratic elements. So that's a very special class of two-sided ideals. We still don't know it in general. However, the ideals are big. The just infinite growth conjecture is now a theorem. So this was Natalia Iudu and myself in 2018. So U of W does have just infinite growth. And furthermore, if I take the enveloping algebra of Virasoro, which has this central element Z, and factor out any Z minus any scalar, that ring also has just infinite growth. So all these rings on this page, U of W and U of Vir factored by Z minus lambda, they're very, very large rings. I mean, U of W, right, looks like polynomials in infinitely many variables with this non-commutative multiplication on it. But somehow ideals in these rings are so large that when you factor them out, they knock this huge ring down to manageable size, down to polynomial growth. And as evidence for ideals being really, really big, remember that the infinitely generated one-sided ideal that we looked at to prove non-Noetherianity was just generated by a single element as a two-sided ideal. So somehow just from this one element, we got all of this stuff. So once we'd answered this question for Virasoro, we started to think, I started to think with other collaborators about other Lie algebras. So let me move over to the affine situation. So this is recent work, really just this year, with myself and Rekha Biswal, who's a postdoc at Edinburgh currently. So start with the finite dimensional simple Lie algebra. Let's just think of G being SL2. Then first of all, the loop algebra of G, its enveloping algebra has just infinite growth, just like the enveloping algebra of the Vit algebra. Very surprisingly, for any non-zero scalar, if I take the enveloping algebra of the affine algebra and factor out Z minus a non-zero scalar, that turns out, I mean, yes, it has ACC on two-sided ideals, but in fact, it doesn't have any two-sided ideals. It's simple. So this was a real shock to us. We didn't expect that in a million years. And actually, even the just infinite growth result was also unexpected to us in the following sense, right? One of the things about the Vit algebra is it's very, very non-commutative. The only time you get a Lie bracket of two elements in the Vit algebra being 0 is when you have a Lie bracket of something with itself. And that has to be 0 because it's anti-symmetric. On the other hand, if I take one of these loop algebras, it has infinite dimensional abelian sub-algebras, right? So in here, I can take any element of my Lie algebra, I can tensor it or multiply it times Laurent polynomials in T, and then the Lie bracket of something in there with something else in there is going to involve the bracket of X with itself and is going to be 0. Now, why do abelian subalgebras, so this is abelian. Why do abelian subalgebras matter? Well, to have just infinite growth, it's a statement that says that two-sided ideals are very, very big. And the thing about two-sided ideals is in a non-commutative ring, right, is if you have some element, say y, and you multiply it by another element x, then both x times y and y times x are in our two-sided ideal. So the fact that the ring is non-commutative tends to make two-sided ideals very, very big. On the other hand, here we've got this big abelian subalgebra where everything commutes. And initially, when we started working on this problem, we thought that all these commuting elements would not allow two-sided ideals to be as big as they needed to be for this theorem to work. And so these are evidence that two-sided ideals are sort of sparse in this enveloping algebra. But very, very recently, as in earlier this week, Alexei Petukov, who is currently visiting me in Edinburgh, we figured out that if you take the enveloping algebra of the loop algebra, or take the enveloping algebra of affine algebra and factor out Z, this doesn't have ACC on two-sided ideals. So that's got a star next to it because it is a very recent result. It's really sort of not ready for prime time. Although I did get Alexei's permission to talk about it here. So if we've got these two sort of structure conjectures on two-sided ideals of these big enveloping algebras, then we know what the answers are for these affine algebras. So in general, though, these structure questions about two-sided ideals, again, they're sort of too hard to answer. So this isn't really a bait and switch. I'm just going to change them into easier questions. But unlike the earlier bait and switch, this is actually going to be genuinely related to the questions about two-sided ideals. So here I want to look at Poisson ideals in the symmetric algebra of a Lie algebra. So let's let L be any Lie algebra, fix some basis, and then the symmetric algebra is just a polynomial ring in this basis. So as a ring, it's just a standard example. It's maybe not that interesting, but it has this additional structure that comes from it being built from a Lie algebra. It's what's called a Poisson algebra. So this is a ring that also has the Lie bracket, which is usually written as curly braces of two elements. And the basic property of this Lie bracket is that it needs to be a derivation in each variable. So it needs to interact well with the multiplicative structure on the ring. And what's this Lie bracket? How do you define it? So I need to be able to Poisson bracket two elements of the symmetric algebra. Well, on elements of the Lie algebra, I know how to combine them. I just use the Lie bracket on the Lie algebra. And in general, I have a polynomial in these xi's. But once I know what a derivation does on a generator, then I can use the Leibniz rule to extend to compute what happens with any two polynomials. So any symmetric algebra of any Lie algebra has this additional structure of being a Poisson algebra. And I said this was not an entire bait and switch because the structure of an enveloping algebra and the Poisson structure on the symmetric algebra, they're closely related. So how are they related? Well, one way to think of the Pbw theorem for enveloping algebras is that if I just think of the enveloping algebra of L as a vector space, then as a vector space, it looks like the symmetric algebra of L. And in fact, I can get more technical and I can say that the symmetric algebra is the associated graded ring of U of L. So I'll just write that as GR of U of L. So what's really going on here is there's what's called a filtration on U of L. And then once you've got a filtration on an algebra, you can canonically take something called the associated graded ring of the filtration, and this gives you another ring. So this is a standard machine. And when you apply it to a universal enveloping algebra, what pops out is the symmetric algebra. Now, I have this machine of associated graded, and I can apply it to, say, two-sided ideals in the enveloping algebra. So I have a two-sided ideal J. I apply this machine and take its associated graded. I get something that's called a Poisson ideal of the symmetric algebra. So what does that mean? Well, this J, it's a two-sided ideal again in the symmetric algebra, but it's also a Lie ideal for this Poisson bracket. So it interacts well with both of the structures on the symmetric algebra. And anytime I have a Poisson ideal that satisfies these properties, I'll write that as triangle sub P, just to have some compact notation for it. And it's a feature of this general machine of starting with a filtered ring and taking the associated graded, that it interacts well with chain conditions. So in particular, if we knew that the symmetric algebra of some Lie algebra satisfied the ascending chain condition on Poisson ideals, it would immediately follow that the enveloping algebra would have ACC on two-sided ideals, which is something, again, that we're very interested in for the Vit algebra and for others of these examples. So I'm not going to tell you everything is known about Poisson ideals of, say, the symmetric algebra of the Virasoro, but let me tell you a little bit about them. So remember, there was this just infinite growth result for central quotients of the enveloping algebra of Virasoro that Natalia Ayudu and I proved. We also showed there's a Poisson version of this. So take a central quotient of the symmetric algebra of Virasoro that still has a Poisson bracket on it, still a Poisson algebra. So I can take a non-trivial Poisson ideal, and then if I factor that out, again, I get a ring that has polynomial growth. This is sort of a Poisson just infinite result. It also turns out that if you have, let me just do this theorem for the Virasoro algebra, you can see it's slightly more general, that the symmetric algebra of the Virasoro algebra has the ACC, the ascending chain condition, on radical Poisson ideals. So this radical here is annoying, right? Remember the previous slide. If we knew that S of Virasoro had ACC on all Poisson ideals, then we would know that the enveloping algebra of Virasoro had ACC on two-sided ideals, which is something we want to know. But unfortunately, all we know is about special Poisson ideals, and this is not good enough. Still, we do get something from these two results. When you combine these two together, this suggests that even though the symmetric algebra of Virasoro is, just as a ring, it's a polynomial ring in infinitely many variables, it's not some place where you would ever want to do something like algebraic geometry. If I start taking these quotients, then I've got ascending chain condition on radical ideals, I've got polynomial growth, I'm starting to look like I might have a coordinate ring of some reasonable variety. So it looks like there might be some algebraic geometry hanging around in the background. And it turns out there is. I'm just going to tell you a very little bit about Poisson ideals, and I'm going to focus on these ideals that are called Poisson primitive. So I want a machine for constructing Poisson ideals. And I'm going to start with some function on the Virasoro algebra, so some function chi from Virasoro to the complex numbers. Then I can build from chi an ideal called the Poisson core of chi. How do I do that? Well, this function is associated just in the usual way to a maximal ideal of the symmetric algebra. And I take this maximal ideal, I'm calling it m chi, and then inside m chi, I'm going to take the maximal Poisson ideal. This gives me a Poisson ideal, which I'll call P of chi. So I can build Poisson ideals using this Poisson core machine. When do I get something interesting? In other words, for which function chi do I get a non-trivial Poisson core? Here, a non-trivial Poisson core, well, if you think about how we built P of chi, z minus chi of z is a Poisson ideal always, it needs to be contained in the maximal ideal associated to chi. So I'm looking for Poisson ideals that are not just generated by Z minus something. And it turns out that we know exactly when this happens. This is Alexei Petukhov and myself last year. There's two conditions. First, let me focus first of all on what happens on Laurent polynomials. Chi, when I want to figure out what chi does to a Laurent polynomial, well, I compute it by evaluating that polynomial, maybe evaluating some derivatives of that polynomial at finitely many points, and then combining them together. So it's a very restrictive class of functions that have non-trivial Poisson cores. Even more surprising, the functions that have non-trivial Poisson cores have to vanish on Z. I mean, a priori, right? I got some arbitrary function from Virasoro to the complex numbers. It could send Z to anything. But if it sends Z to anything non-zero, then the Poisson core is boring. And from this sort of structure result on Poisson cores, we get that if I take Z minus any non-zero scalar, that has to be a maximal Poisson ideal. In other words, another way to say that, right, is if I take the symmetric algebra of Virasoro, factor out Z minus lambda, it's Poisson simple. So this is just an illustration of knowing a lot about the Poisson ideals of the symmetric algebra of Virasoro. And because of the close relation between Poisson ideals and in the symmetric algebra and two-sided ideals in the enveloping algebra, this suggests that the enveloping algebra factored by Z minus some non-zero scalar should also be simple for lambda non-zero. So I think the answer to this question is yes. And this is a question I asked earlier for the Vit algebra, but clearly we can ask it also for Virasoro. Does the enveloping algebra of Virasoro have ACC on two-sided ideals? We don't know if there's ACC on Poisson ideals. We know there's ACC on nice Poisson ideals. Again, I think the answer to this question is yes, but a word of caution, right? For affine algebras, okay, the corresponding, the simplicity of non-trivial central quotients, that's known, the answer is yes. But the ACC, the answer is known again, and it's no. So this is maybe like a grain of salt. Maybe my intuition here is inaccurate. As evidence for my intuition being okay, I'm going to remind you that the enveloping algebra of Virasoro is much more non-commutative than the enveloping algebra of an affine algebra. And so two-sided ideals should be a lot bigger in the enveloping algebra of Virasoro. So it's, in other words, since two-sided ideals are big in U of G hat modulo Z minus lambda, it's maybe reasonable to think they're also big, so big that they have to be the whole ring, right, in U of Virasoro mod Z minus lambda. And then on the other hand, I just think the answer to the second question is yes, even though the answer for affine algebras is no. Again, there's no reason that just because it's no in the more Abelian algebra, it has to stay no in the non-commutative algebra. Okay, that's what I had prepared to say. Thanks very much for your time and for listening to my document.